All right, let's see efficiency of your code. Now, let's look at what the textbook has here first. So we said we use big O notation to obtain a function for measuring the algorithm's time complexity based on the input size. Yes. And now when you look at that, let's look at, for example, let me see if they have example code first. Like this code. So look at what should be the big O for this. How would you do that, right? So we said, okay, look at n is the size, right? N is the size. How many times that you're going to loop for this, depending on n, right? And every time you're gonna add 5 to k. K pretty much just a variables, right? And we're gonna spend a time to execute this lab code. And we said, okay, assume that it's gonna take about c constant time. So depending on the speed of your CPU, right? Different CPU have different speed, right? So that's why we call C. And we said we can put this into the function called Tn, like time, right? Depending on the size, because we don't know how many n. Like if I want to increment by 5, if I want to do 100 times, then n could be T100, right? Pretty much how long it's going to take is 100 times that C time, right? Then if it's take about 5 seconds every loop, so 500 is the answer, right? That makes sense? Like I said, depending on the CPU, that CPU could take only 1 second instead of 5 seconds, right? Then 100 instead. All right, so let's come back. So we see that's just an overview, right? So it said it depending on the input size. We just mentioned that. Now you can also ignore multiplicative constants and non-dominating terms in the function. So let's say, for example, let's look at the function again. Let's look at example. All right. So this happened to put the function that we look at, right, into the program and try to write a code to test. So to test this code, pretty much passing the number of n, right, into the function, and look at the output, how long it's going to take. So it's pretty much just get the current system time, right, using system.current_time in milliseconds, right? So we're going to subtract the end time to starting time, right? We have start time and end time. Then we return like how long it's going to take depending on the size, right? Now let's look at another example. So we said the first one loop is going to take about n, correct? Because the size of n. And how about the second one? So we have 2 loops. This is nested loop, right? We start from I equals to 1 to the size of n and j equals to 1 to the size of n. And in the second loop, inside we do k plus I plus j. So it looks like we have to do this n time, right? The inner loop, correct? And then once we're done with that n times, we have to do this another n time. So this is going to be n squared. It's just like n times n, correct? And again, c is the time it's going to take for each loop, right? So it's about n squared. Now, when you see this, we call it quadratic algorithms. Like in math, we call quadratic functions, right? So with the exponent, so that's why we call quadratic algorithms. So the first one pretty much is just like a linear, right? A linear, right? N, right? So let's look at this example, the third one. So the third one, the difference is, if you look at the loop here, right? Before this is n and n, right? Now the third one is the second loop depending on the I, right? Of the first loop. So would that affecting the efficiency? So what's I always increasing by 1. So this pretty much just this loop no longer do n but do I instead, right? So it's actually, it looks like it's going to reduce some time, right? Because you not completely do the whole n, right? But let's see how we're going to measure that. So it said, so the outer loop executing about n times for I equals to 1 to the n. The inner loop is executed 1 times, 2 times, up to n times, because it's depending on I instead, right? When I equals to 1, is execute 1, right? So that means this is a sequence, right? So that's why I start to do, first one is about C, because 1 times 1, right? And then start to increase like 2 times 1, 3 times 1, until n, right? So that means math is going to help now. We're going to do the sequence, right? You can see you can put a constant out. And then it's like 1 plus 2 plus 3 plus 4 is about n plus. So an, right? This is an Sn, actually Sn in algebra, right? Sn. And Sn formula pretty much just has what? If you check, just check. Sn formula, right? This is the arithmetic series, right? So Sn equals to, let me just look at the formula here. This is a formula for geometrics when it's multiplied, but we look at arithmetic. Arithmetic should be this one, right? So it's a Sn equals to n times 2 a, this is like an, or the first one, plus a minus 1 times d divided by 2. So technically we put that formula in, we're going to get something like this, right? And then we just simplify the function. And then after we simplify it, this is it. This is the one that we're looking at. So we said it's going to take about the constant c over 2 n squared plus c over 2n. Now when we get to that point, the question is, come back to the definition. So the definition says you can ignore the multiplicative constants. That means the first portion that we're looking at, right? Or we call the coefficients, right? The c divided by 2. We can actually ignore that. And non-dominating terms. The non-dominating term is the half part to the right, that plus. Okay, let me do the screenshot for this one and go back to the formula itself. I want to go to take the snapshot of this definitions of the big O. Alright, so we go back down to the function itself. So that's it, right? So let's read this part again. It says you can ignore the multiplicative constant. That means c over 2, we can ignore it. And also the non-dominating terms. So if you look at n squared, let's say if I have n equals to 1 million, n squared is going to be 1 million times 1 million, right? About 10 to the 16, right? No, 10 to 12, right? Because you add the exponents, right? Correct? So, but if you look at c over 2 times 1 million is about what? 10 to the 6. So when you add 10 to 12 to 10 to the 6, we talk about 10 to 12 is about, what do you call that? What's 10 to 12? Giga is what? Mega is 10 to the 6. Giga is 10 to the 9. Tera. We talk about matrix, right? 10 to the 6, 10 kilo is 10 to the 3, right? You guys still remember that? Let me show you the matrix system, right? Prefixes right there. Like kilo is 10 to the 3, right? 1000, correct? 1 million is called mega. 10 to the 6. And we talk about 10 to the 12 is terabyte. Tera, right? Now, when you look at tera add to mega, it's just like 10 and then 100. Just like I'm buying maybe an island at $1 tera. Okay, and the owner of the island want to sell me at $1 tera and $1 million. I said just do $1 tera then. Just give me a discount. Correct that? And if you want the money, it's just okay, I'll go for it. Because this is called non-dominating terms. You can actually ignore that small portion because you want to go with a big portion. Make sense? So that's why it's become too big O n squared. Like we can look at, take the non-domination or dominating terms out, and then look at the terms they call ignore multiplicative constants, right? That makes sense? So that's how you look at the big O. Okay? So in the test, you're going to see this.
Which one's the non-dominating?
This is the non-dominating terms. Because it's only million, I'm telling you, its example is 1 million as the size of n, right? It's just the same thing if I just do 100. This is going to be about 100. So let's say if c is 1, so it's about just 50, correct? But 100 squared is going to be what?
10,000.
100,000, is it right? Or 10,000?
10,000.
It's 100 squared is about 100 times 100, you have 4 0, about 10,000. So 10,000, okay, you divide by 2, like say c is 1, right? So you divide by 2, you have about what? 5,000. So 5,050. So you buy a car at $5,050. Would you say, hey, I just want to pay 5,000? Would you sell the car? And you say, yeah, let's go for it. Because you don't really want to actually just get $50 off and you're not selling the car, right? So that is the $50 itself is the non-dominating terms. When you measure it, it says it's about 5,000 efficiency, right? Okay, that's why we can ignore it. That makes sense? All right, that's the same thing. Now let's look at example 4. Now, when you look at nested loop, be careful. You may be tricked that, hey, it's nested loop. It's going to be about n squared. It's not always true because look, this is only limit to 20. So 20 meaning it's just the multiplicative term, right? It's always loop by n and times c and times 20. So it's actually just big of n because you can just ignore the multiplicative terms, right? According to the definition of big O, right? Any questions? Look at example 5. Can you tell me what should be the big O? And this is pretty much going to be on your test of this. We have a sample program. Tell me the big O. Technically, Teddy asked for the review. This is part of the review already.
Plus NC times 20.
Okay, you say n? Yeah. 10 times c plus 20 times c times n. So we said this is going to be your dominant term, right? Which we can just ignore it. And this is going to be your multiplicative, right? Which we can ignore it. Then we get n. And that's how you measure, right? Your efficiency of your code. Efficiency of your code. How about this one?
The size of your list.
I just want to see, is it n or n squared, right? That's the answer I'm looking for, or 1. 1 meaning you not really spend too much time. It's only run once. That's it.
So it should be n. Here.
So you say n?
Yeah.
Why is it?
Because going through the list 10 times.
You talk about this one?
For each, yeah. For each.
That's going to take n, okay, to each, right, t.
Yeah, for
And
each.
what happened to this one?
It's just one of it. So we don't consider it. So it's not a loop.
Contains. How would you implement contains? Okay, how would you implement it to search? We just talk about linear search. If you do like just linear search, it's gonna be n. If you do binary search, it's gonna be log n. So would you consider that into the equation too? Pretty much yes. It say list dot contains is going to take about n, so this means it's linear search, right? But since it's not nested loop, then you do plus, right? If test time, right? It's take about n here, correct? And then you get a loop to print this out, right? The loop in the else clause take about another n, right? So you said this is about n, and this is about n, so you have 2 big O of n, right? Now when you add, you get what? Pretty much 2 big O of n, right? And then 2 is pretty much just the multiplicative term that you can ignore, right? Then we get n.
So instead of using n, is there any problem that just with numbers?
If it's multiplicative term, is you can ignore, right? I mean multiplicative like coefficients or the dominating terms you can ignore, right?
Okay, for example, if we just set for a carbon on the top of the pages, can we just say
Where do you want to put 4?
no, the top one?
This part?
No, the other one.
This
All the way top.
top?
Yeah, for
You top of this?
yeah, only that part. This is the what they call.
It's already have 4, right? You talk about this 4, it's already have 4. Because nested in there, right?
Yeah, but I'm talking one with the number, not n.
Oh, this, not n.
Not that, not n. So can we just say it's gonna go to the 2? So the
If you put this 20,
Maybe
does that mean 20 times 20? But
I think
how would you measure then if you never have n? Because depending on the function of n, right?
so there's no the annotation without n.
I mean, it's going to just be constant. Like, that's going to be about 410,
Okay.
right?
Yeah.
It's going to be a constant time. But it depends on how you compare with. If you say 410 compared with billion, then 410 is so fast. We can make it as a constant time, which is, we say big of 1. Not n, it's going to be 1. But it depends on how you compare it with, right? If you compare 410 to billion, then 410 is just, you can say it's constant time, big of 1. But if you compare 410 as a size n equals to 20, then it's big of n. Let's look at another example, 7. So, all right. So how long it's going to take? We talk about this one, right? And then so it's a what we try to do, we try to multiply a, right? So this look like an an, right? For the n times, so it's like an an. So we say it's going to loop about n times, so big O of n. Okay. I said, assume n equals 2 to the k, So this, if say n equals 2 to the k, if k is 0, we get n equals to 1, right? If k is 2, we get n equals to 4. So technically this is gonna loop like depending on the k, right? Not n anymore, right? This one is depending on the n, right? So meaning that if it's depending on the k, that means you reduce the time by half, right? Because n equals 2 to the k, like I said, if k equals to 2, and it's gonna be 4, that means this is gonna loop 4 times, correct? But this is gonna loop just 2 times, correct? Because depending on the k, correct? So if k equals to 3, so it's gonna be n equals to 8. So it's about half, right? So it's about what? Exponential. This is exponential. So if you still remember graph of exponential, right? So we know that the opposite of exponential is logarithms, right? If you still remember the basic math, right? Algebra. Let's look at, these are the logarithms and this is the exponential. Try to reduce the size a little bit to make sure it's fit in one page. So exponential said it's going to grow very fast when your n is very small, correct? Like 2 to 0 is 1, 2 to 1 is 2. It's going to grow like very fast. But for the logarithm it said, but it's very slow, right? You see, it's when your n is increasing, but it's going to grow very slow, right? But that one's grow very fast. That was the definition mean, right? So we just rebuild the math. Now come back to this. You see that n is going to grow very big, right? But k is going to be very small, right? So meaning that if I change this, even we have big K, this is going to take like way a lot longer than this, correct? Like if K is 100, it's going to loop like about 100 times, but it's going to be 2 to the 100, which is a lot. Let's see what's 2 to the 100 giving you. 2 to the, I have to use the scientifics, 2 to the 100. You see that? This is going to take forever, right? But this is done already in, right? So this algorithm takes only big of log n, but this is going to be n by just changing to k when n equals to 2 to the k. That makes sense? Any questions? So that's why you want to practice on this type of questions. Otherwise on the test you may just start, hey, this is going to be n, but I have to be given n equals to 2 to the k. So It's not going to be n, it's going to be log n.
So I'm confused. If you just, all you have to really do is what? Switch the n, okay?
Right, but it has said n is the size of your array, right? Or size of the list, right? Size the data, like we talk about list, right? This could contain 100,000 millions, right? So n is the size of the list. Now, if we want to search for an item in the n, it's going to take about n if you use these algorithms, correct? But if you happen to have the algorithms that say, hey, n actually can be reduced by 2 to the k, and we can search by k to get a result, it's reduced to log n right away. Which log n is way a lot faster. It's only take 100 cycle, you got the answer. But this one would take I don't even know what's that. This is mega tera. We have to see the prefix. Like maybe a lot more cycles just to get to a result. So would you prefer this in your program or this?
The bottom one.
Right. This is an efficiency code. We talk about like Google search, right? If you type in a keyword, if Google do this, who's going to use Google? But Google happen to give you this. That's why people use Google, right? That makes sense? Then you get the result right away based on the key. And the key actually searching against, like Google actually searching data against what? N size. And the N size yeah, it's like all the data in the world, right? It's like infinite when I type in the word. If I want, look, I just type in the word metric system. It just give me the right result right away. But the metrics could be meaning so many things in the world, right? But the results only take about maybe even better than log n.
So I'm confused. Is it just
It's just do the like matching to 1 right away for me. That's a constant time.
So the difference in that code is just the n or the k, or
The difference in the code? Yeah,
100%
like
understanding?
this is linear search, right?
Is it because the result equals a on the bottom one? Is that like?
Result equals to 1. This is just initializing, right? And then it just keep multiplying a to itself and give the result to the answer of a. But now by giving result equals to a, because we know it's going to be a times a, that's why why don't we just do this? It's going to give you the same result right away. But this code is going to take you longer than this one. But just think differently, right? Like this one will give you a result. Like if I ask you to write a program to find like the multiplication of a, most likely you're going to think it this way. You just say, hey, how many times? N times, just loop start from 1 to n. Correct? You actually give me this right away. But like I said, if my n is how many times? It depends, right? Like if I want to get hundreds of them, it's going to take me 100 times, right? But look, this is going to give you the same result. Instead of initialize result is equal to 1, I just initialize result equals to n. I mean to a. Right, and then we just say a times a for the k's time because we know that it's going to be depending on the k. You got it? by taking log 100, right? Because n is 100, right? This one is log base 2, right? So by taking, can I do log base 2 here, right? How do I do log base 2 on this one? I guess I have to switch to programmer now. Okay, maybe Google is faster. Like log base 2 of 100. It should give me a result, right? Yeah, of 100. It's gonna take only 6 cycles instead of 100 cycles to give you the answer, and you get the same answer. But I just think differently. And how many of people will really get to think and write a code this way? Only people who knows math. I know, like, not just know, but really understand how it works. So that's why computer science, if depending on the math a lot. Okay. Because math actually solve a lot of issues by reducing the time. Right, these two algorithms give you the same result, but this one is only takes 6 cycles. This one will take 100 cycles to get a result. So this is the difference between what Google, Bing, Yahoo, and other search engines. That's why if you want to work for Google, you have to think this way, huh? When you write a code. If you write a code this way, you never work for Google. Right? They can just give you the interview test questions, just simple, and see how you write the algorithms. Then we're gonna work for Nova like me then. All right, so understand. So this is just checkpoints that you can read this, okay, for your review for the test. It's gonna help. And also, I want you to start to download this one. Okay, and bring it back next class. I have the practice for you. Big O exercises. Let me see.
Is that the top?
I think it's at the top.
Is that the top?
Yeah.
Yeah. First one.
Oh yeah, thank you. Well, I happen to give you answer key, so that don't look at the answer key yet then. Should I remove it now? Huh? I should remove it now, right? Let's see, some of you try to download it. Huh?
No.
Just leave it.
Okay, I'll leave it. Alright. But I want you to practice doing it. Can I just hide it?
Sure.
I don't know why. We should be able to hide it, huh?
But we're not gonna look at it.
I mean, are we going to need the answer key to check our answers?
Yeah, to check on answers.
Yeah, do we need it?
To make sure we got it right? So I'm not just sitting there like, oh my god, did I get it right? Or am I...
But answer key could be wrong.
So why is the answer key wrong?
The answer key. It's supposed to be right.
It could be wrong, yeah, I'm telling you. Why? Because I'm making it. And I could be wrong because I'm human. Human has error.
True.
Could be.
But I don't think you'd be wrong on all of them.
Yeah, the majority should be right.
So don't trust the answer key. If you took my CSC202, you know that.
Yeah, that's what I'm saying. We get extra credit if we find any mistakes.
You're actually gonna get the good practice for your exercise for midterm. If you can find it incorrect, and then we're gonna talk about that next class. Okay, so just download that. Okay, the second one, and try to do it first, and try to tell me if this answer key is correct or right, not. And we're gonna discuss that in class. Okay, they don't have to worry about answer key because I think it may be wrong. Yeah. And I mean, I have some video to explain that. All right, so practice that. All right, let's look at the question a little bit. You'll see it's pretty much something that you may see something very similar in your test. Okay. See, it could be just the expressions like that one. You should know right away, right? Into the fourth, right? Big up into the fourth right away because this is the dominant terms, right? We can ignore, and this is the multiplicative, right? Terms we can ignore. But we have some like exercises like the loops that you have to consider what should be the big O. Okay. All right, do that. Bring it back this class, next class, for your review. And these are all the checkpoints that can help you to find big O. Same thing to practice for your test. So go back, do this one too, okay? And we come back and talk about it. The checkpoints, page 826 and 827, okay? All right, so let me send that on announcement, then you know. All right, so review big O. What page? 827, right?
26, page 27.
Okay. Daniel Lang, page 826 to 827, checkpoint. Okay, for big O notation. And also at the big O notation exercise worksheet. Okay, under course document. All right.
In the subject, the big, like you misspelled the big word in the subject. Like
All right, so you have that note on the email. So any question on big O? Now let's look at how about we talk about search, right? If it's linear search, we loop all the way through beginning to the end. It's gonna take about what? What big O? N times. Now if I do binary search, how long it's gonna take? I just change to binary search. And we talk about how you implement the binary search. You already told me that you're gonna go in half and half every time you search. So it said here, let's see, it said first time for each iteration in the algorithm contains a fixed number of operations denoted by C. And let's Tn denote the time complexity for a binary search on a list of n elements. Assume n is the power of 2 and k. So it's just the same principle like we just looked at. It's always reduced by half and half and half, right?
Then go into n.
Right? And say, since a binary search eliminates half of the input after 2 comparisons, so we said, so it's gonna look like this. You're gonna go to what? First time you do half, and you're gonna do half of the half, right? To n divided by 2 to square, right? And then you're gonna do another 2 to the k, right? And c is what? Kind of a fixed number of operations. So every time when you call it, you're gonna have increasing your operations from 1 to 2c and 2kc. So technically it's gonna look like this, right? Which we said k is about to equals to log n. So that's why we substitute that. And we see log n, this is going to be n over n, right? Because 2 to the power of log n is the logarithm's formulas. It's going to be n, right? And then n divided by n is t equals to 1 plus c log n. And we have the reason why k equals to log n. We talked about exponents time earlier, right? From the previous example. Then we pretty much just change, right? Simplify it to t1 equals to t1 plus c log n. And then t1 pretty much just 1 and then log n. So this is a constant part, right? Then we technically can eliminating the non-dominant term and then the multiplicative term. So we have big of log n left. So that's why binary searches take about log n. Questions? How about selection sort? All right, so there's many techniques when you do. We said binary search, we cannot search when the list is unsorted. So part of the search itself take about log n in the case that it's sorted list. But to make it sorted, it's going to take longer, right? So to sort, how will you sort? There are many techniques to sort. If you learn from 200, 201, you may start to learn how to sort the list a little bit. So how will you sort? Can you tell me algorithms to sort or how to write a program? How would it take to after that? Like what's the big goal of that program?
Sort an array in
Right, so you have a list of array. How would you sort an array? You have to compare the first one to the second one.
and then if it's less than the second one, you're gonna assign it to the third, send it like don't change their places, and then go again and again and again. If it's greater, you're gonna change the places a little.
Okay, you're going to change the location, right? So how many loops do you need in that case?
Is it n over n? I mean n exponent n to the n.
N to the n. N to the n is a lot. So how many loops do you need to sort the list?
2 loops. Wait.
Okay, if it's 2 loops, then what's the big O?
N.
N square.
Oh wait.
N square.
N squared.
One loop is N, right?
Mm.
So it's about N square if you talk about that, right? Now let's talk about sort technique. Let's review the sorting technique. Sorting. So we have an array. This is an unsorted list, right? And we try to sort it. And we said this technique to sort. First one we call selection sort. We also have bubble sort. We also have insertion sort. So these sorts are not complex, but they're not efficient. Right? Where it's not complex, it's not efficient. Where it's complex, it's more efficient. Easy to understand and to implement. So selection sorts, the techniques say you select the name that come first in the alphabetical order and write it on the second sheet of paper. Let's look at this. Like I want to sort the list. You try to look at alphabetically order. H is the one that come before the rest, right? That's why we select it and just rewrite in the new list, right? Now we cross that out. We look at another and we see, okay, M should be the next one. I and C should come first. So we cross this and we put McCarthy. We do the same thing, repeating over and over again. All right, when I select the one that's the lowest on the list, how do I implement it in? I need a loop to iterate to it and find the smallest. That's one loop. And I pick it, find the smallest. Because I have to compare everything one by one to the end, right? It takes one loop, right? But I'm not sorted yet. So that's why I have to repeat the same step for the remainders. That's another loop. That's why we need 2 nested loops. It has to be nested too, right? Remember, if it's not nested, it's just n plus n to n. If it's nested, it's n times n squared, right? It has to be nested because we keep repeating the same list and do the same thing over and over again, find the smallest, right? And the list size is getting smaller and smaller, right? It's about n squared, we see that, right? By doing selection sort. That makes sense? So, come back to the book. So it's saying that, okay, binary search times to take to search about log n. And if I want to do selection sort the list is about n squared. And we agree with that, right? 2 loops, right? So if you combine them together, if you have to sort n squared and search log n. Okay. This is we were talking about the Tower of Hanoi, right? Tower of Hanoi, we know what it is. They just try to analyze. Like for example, I want to see what's the big O of that algorithm, and we know that we have to move the first n-1 disk from A to C, use B as the auxiliary, and move the disk from N from A to B. We're repeating that over and over again. And n-1 disk from C to B, right? I mean, you can go back and review that code. So the Tower of Hanoi is an example of big O of 2 to the n. Okay, so we just try to, let's just simplify this. Okay, when we get about 2 to the n minus 1, and we have to go with 2 to the n. Okay, because h n minus 1 is going to take about t n minus 1. This step just take 1, and that's another n minus 1. So about t n minus 1. That's going to give you 2 to the t n minus 1 plus 1. And we try to simplify these equations. Because this is like, if you remember, we have to call itself over and over again. We use recursive, right? So that's why this is try to break it out a little bit. When it pass n minus 2, n minus 3, it's going to keep doing like that. So that's why we do the 2 to the n minus 1 as exponents of 2. Because this is recursive question, we use functions called itself over and over again, and itself takes about, right, n minus 1, n minus 2, depending on the size. So that's why it's going to take about this after we simplify it. And that's why it's come about 2 to n. So that means if we write a program about recursive, like I said, recursive is better in terms of reduced complexity of the code, but it's not better than iterative, right? Iterative with the loop, right? It's going to be less time, more efficient. Recursive is going to take more time, less efficient. But some problem you cannot solve with iterative way, or it's just going to be too complex to iterative way. Then we have to trade that up with efficiency. And it's going to take about 2 to the n. And we see the exponential graph. It's going to take forever when the size is very small. Okay. So we actually try to stay away of using recursion. Maybe we can get to the solution. So the common recurrent relations, these are the useful tool for analyzing algorithm complexity. Like, for example, the complexity for binary search, selection sort, and the Tower of Hanoi, we can see the sequence like that, right? This is the binary search, always in half. This is for the selection sort. And this is for the Tower of Hanoi, right? So we can see this is called recurrence relation. So whenever you see something like this, it's like log n, right? And those are example binary search. And you could create common denominator. This is like linear search, where you see term like this. You see half, this is like log n. This is like this is like n. When you see 2 to tn, this is about n. And when you see like this, is about 2 to n. This is also 2 to the n, right? Fibonacci recursive algorithms. This is selection sort. You may see it's just used like if you love math, so simplification of math giving you this, right? Simplifying. Now let's compare. So we see that we have what constant time, like I tell you, when is about 1. And that's pretty much Nasmil, you have the question, what happened if I change that into 20, right? This is like you change into 25 or into 50. We just said when you know the constant is about 1, right? If your program have the constant, not depending on n, that means constant time. So, but if your program has n, so then if it's a like logarithmic time, example just like Bernie search, then when the size of the function is what? 25 is take about 4.64, which if it's linear time, it's going to be 25, right? This is about 1 loop, right? And if it's n log n, this is log linear time, it's about 116. But if n square is what's example? The selection sort, right? It's gonna take about 625. But if you look at 50, but it's 50 is turned to 2,500. But log n is only 5.64. If you talk about quadratic time, right, it could be the cubic. It's gonna take a lot, only 50. But if you talk about exponential, like we can see the small n it is, it's gonna take like forever. And this is the graph to represent that, right? This is like quadratic or exponential. This is quadratic, cubic, this square, log n, and constant is that means no matter size of n is always 1. That makes sense?
So it means we want to achieve, so it's always constant time.
That's a goal that we want. Just like Google search, you search and you get it right away. Right?
Because it's constant time?
The most likely is return the topic that relevant as a constant time, right? Which, how we gonna get to that? Which we can find out from Google algorithms. So algorithm is should be secret, huh? But if you can just think about that, you can be a billionaire, right? That's what it is, right? All right, so I think it's about time. So I want you to go back and pretty much just review that section, okay? And now you understand what it is. Go to do exercises and we come back, okay? And look at more into chapter 22. All right? We just stop at this graph for today.
Hey, Professor, for homework 21, which book are we supposed to use